Hey guys, welcome back. Today we're going to talk about lesson 2.1, limit definitions and rules. So this is our first calculus concept. So limits is going to form the basis of everything else that we talk about in calculus. So let's get cooking, talking about some limit definitions and rules. So first is the notation. So the way that we read this, and I'll write this out as we read it, the limit of f of x as x approaches c is equal to L. So basically what this means is as x gets really close to a specific value, the function is going to approach some value that is the limit if it exists. So for example, if I had like the limit of 3x minus 1 as x approaches 2, we know that this graph is linear, so it's going to approach some specific value, and that value will be 5 because this function is going to approach a value of 5 as x approaches 2. So we're going to look at a graphical representation of this. So here's one where I'm finding the limit of x cubed minus 1 over x minus 1 as x approaches 1. In this case, I'm not 100% sure what this graph is going to look like, but I do know that as x approaches 1, I have an issue because 1 minus 1 is 0 and I can't divide by 0. So what I've done, and we will figure out a way to solve that problem, but right here, I've shown you what the graph of this looks like. And if you notice the zoomed in portion, at 1, there is a hole in the graph with a y value of 3. So important thing to note here is that even though 3 is not a value that actually exists in the graph, the limit is still equal to 3 because remember, limits are just about what value the function approaches. It's not the value of the function itself, it's the value the function approaches. So as x approaches 1, this function approaches 3. So the limit is 3. So there are 3 situations where limit doesn't exist, and I'm going to show you examples of what each one of these looks like. The first one is that if f of x approaches different numbers from the right and the left, that's going to be called a jump discontinuity. If f of x increases or decreases without bound as x approaches c, that's when the function is unbounded. What that's going to look like is going to be a vertical asymptote on the graph, or when f of x oscillates rapidly. So I'm going to show you an example where f of x is going to oscillate rapidly around a specific x value. So first, let's look at the jump. So let's take this function absolute value of x over x. If I think about the graph of this function, if x is positive, then I get a value of 1. If x is negative, then I get a value of -1. So the graph is going to look something like this. X cannot be equal to 0, so I have open points at each of those places. But what's different from the holes here and the hole in this graph is that if you notice in this graph, I'm still approaching the same value for both sides of the x value in question. So I'm still approaching 3 from both sides. But in this case, from the right of 0, I'm approaching 1. From the left, I'm approaching -1. So this limit does not exist because I'm approaching 2 different values. So now let's take a look at an unbounded example. So I want to think about what the graph of this function would look like. So notice all of these limits that we're doing right now, we're kind of doing them graphically. We're imagining what the graph would look like. There's going to be 3 different ways we're going to do limits, and it's going to be graphically, tabularly. So we're going to use a table to figure out what the limit would be, and then analytically. So all 3 ways are going to be different ways that we find limits. For today, we're focusing on graphically first. So this graph, as x approaches 0, basically what's going to happen, we know what the graph of this looks like. On the right side, it's going to look something like this. This function is even, so we can reflect it over the y-axis. And this graph is going to look something like this. And if I notice as x approaches 0, I have a vertical asymptote for this function. So from the left and right side, this is approaching infinity, which means this limit does not exist because even though we're technically approaching the same value, being infinity on both sides, we can never actually be equal to infinity. Infinity is a concept, so we can't ever actually be equal to it. So this limit does not exist. So now we're going to look at the oscillating example. So I'm not going to attempt to draw this graph on my own because it's just going to be a whole bunch of squiggles. So I have the graph down here. But first, we're going to talk about what the concept of this graph is. Basically, as x approaches 0, this quantity right here, 1 over x, approaches infinity. As this approaches infinity, sine, which we know is periodic, sine is going to move rapidly between -1 and 1 because that is the maximum and minimum value of sine. So as 0 gets smaller and smaller, sine is going to move through its period much quicker, and it's going to end up with a graph that looks like this. So as I approach 0, what happens with the function is it's actually oscillating very quickly between -1 and 1, which means there's no specific value that the function is approaching, so this limit doesn't exist. So far we've had the definition of a limit as x approaches some value, f of x approaches some value. And that's a good definition, but what we want to do is we want to put a little bit more rigor on it. We want to make it a little bit stronger. So we're going to talk about the epsilon delta definition of a limit. So basically, here's what we're going to do with the epsilon delta definition is the value of fx is arbitrarily close to L. All of this right here is the statement of this epsilon delta definition. Basically, what this statement right here is telling me is that for any number epsilon, so I can let epsilon be as small as I want. For any very small positive number epsilon, there is some delta that will get us that close to the limit. So this is the technical definition, and then x approaches c, this is technically what it means. So let's take a look at what this means graphically. So graphically, what this is telling us is basically, you can tell me any epsilon that you want to. So here's the limit plus epsilon, the limit minus epsilon. If the function is continuous and the limit exists, then no matter how close you want me to get to the limit, there is some number delta that I can use for the x value that will get me that close. There's some number delta that will get me that close to c, that will get the function f of x that close to L. So the way that these problems are going to work is basically they're going to give you an epsilon and say find the delta. So here's an example. So I'm looking at this limit. I want to find a delta such that f of x minus L is less than 0.009. Basically what's happening here is this function is saying I want to be within 0.009 units of L. Either above or below, I want to be within 0.009 units of L. In order to do that, how close do I need to be to 3? So how close do I need to be to the c value of 3 in order for the function 0.009 units of L? So what we're going to do is we have this statement. Our goal is to take this statement and make it look like this so that I can establish what delta is equal to. So here's what I do. I've got absolute value of f of x minus L is less than 0.009. So this is my goal. I want f of x to be within 0.009 units of L. So also, I know that 0 is less than this because f of x is not actually equal to L. Remember, I'm approaching L. So 0 has to be less than whatever this absolute value. So I've got 0 is less than, f of x was 3x minus 4. The limit is 5, and that's less than 0.009. So now I'm going to simplify what's inside the absolute value. This absolute value of 3x minus 9 is less than 0.009. So my goal is to make it look like this. So I notice I can factor a 3 out. So 0 is less than 3. Absolute value of x minus 3 is less than 0.009. Now I can divide by 3. Left with 0 is less than the absolute value of x minus 3, which is less than 0.003. I've now taken this and established that 0 is less than the absolute value of x minus 3, which is less than 0.003, which means that delta, so delta, that's a terrible delta, but you know what that is. In this case, would be equal to 0.003. In other words, what that tells me is if I want my function to be within 0.009 units of the limit, then I need my x value to be within 0.003 units of c. So we're going to take that. That is our rigorous definition of a limit. AB, I would expect you to be familiar with this, understand the concept. BC, I would expect you to be able to find delta if I give you any specific epsilon value. So properties of limits, I'm not going to sit here and read through every single one of these properties. If you need to, you can pause the video and write down these properties, but these are just some properties of limits that will apply whenever you're trying to find the value of a limit. So here's an example of something that we can do. We're only going to do this first example. We're going to work through some more examples in class. So if you have any questions, you can ask them. But we're just going to work through this first example right here. So what I can do here is I have the limit as x approaches 3 of this whole statement right here. Using the properties of limits, I can break this down to limit as x approaches 3 of f of x minus 4 times limit as x approaches 3 of g of x. Now this makes my life a lot easier because I know the limit is x approaches 3 of f of x. That's 8. So this is 2 times 8 minus 4 times the limit as x approaches 3 of g of x is negative 2. So this is 16 plus 8, which is 24. So again, we're going to practice in class with applying some of these limit properties. But if you have any questions about this, feel free to bring them to class. So last thing that we're going to talk about is the squeeze theorem. So the squeeze theorem is basically the idea that if I have this function f of x that is between the functions g of x and h of x, then if the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x, then the limit as x approaches c of f of x must be the same. So this makes sense because let's say that I have this function g of x down here. So here's g of x. And then I've got this function f of x that is always greater than or equal to g of x. And then I have a third function, which we'll call h of x, which is always greater than or equal to f of x. I can see from this example that f of x is always between or equal to these two functions. If these two functions, g of x and h of x, have the same limit at any point, then it must be that f of x has the same limit because it would have to be equal to these other two values. So let's take a look at this. And we're going to try to find the limit as x approaches negative 1 of g of x based on this information right here. So first, let's look at the limit of this function on the left side, and that would be 3. Then let's look at the limit of this function over here. In this case, we can actually just plug in the values for x, because if I just plug in the values for x, these are polynomial functions. I know that they're continuous everywhere. There's no holes. There's no other kind of domain issues to worry about. So whatever the value is when I substitute in negative 1, that is the value of the limit. So for this one, I have 3 is less than or equal to g of 1, or g of negative 1, sorry, which is less than or equal to negative 1 squared is 1, minus 1, plus 3. 1 minus 1 is 0, plus 3 is 3. So therefore, the limit as x approaches negative 1 of g of x must be equal to 3. Because the value of these two functions, sorry, let me back up a second. This is not necessarily less than the value of g of 1, but it is less than or equal to the limit as x approaches negative 1 of g of x. So because I know that both of these limits are 3 and g of x is between those two, then it must be the limit of g of x is also 3. So that is it for today's lesson. These are the topics. I hope you took some good notes. I hope that you come to class ready with some questions, and I hope you have a fantastic day. I'll see you next time.